Welcome to the Faculty Forum Online, a program of the MIT Alumni Association, sponsored in part by MIT Professional Education. I'm Judy Cole, and I'm the Executive Vice President and CEO of the MIT Alumni Association, and I will serve as the moderator. Alumni who wish to ask a question of our guest today, please fill out the form on your screen under the webcast. We will try to answer as many questions as possible. It is my pleasure to introduce to you Professor Nergis Mavalvala, the Curtis and Kathleen Marble Professor of Astrophysics and Associate Department Head of the Physics Department. If you haven't followed the news from the Laser Interferometer Gravitational Wave Observatory, a 2-decade-old joint venture among MIT, Caltech, and 80 other research institutions around the world, you are in for a treat today, nearly a year since the first detection of gravitational waves, and with it, the proof of Einstein's 1916 prediction of their existence. We are joined by a woman who has devoted her entire academic career to identifying, measuring, and verifying Einstein's hypothesis. Professor Mavalvala, I hope you can start by giving our alumni, physicists and non-physicists alike, a general understanding of your work. We would also love to hear the story of where you were and what your first reaction was on hearing the news of the detection last September.
So thank you, Judy, and thank you to everyone out there who's online and listening. So I think what I'd like to do is I'd like to start with a little journey. And our journey actually begins several hundred years ago with Newton. So to understand the measurement that was made by LIGO, we sort of need to dial the clock back to Newton and his ideas of gravity. So Newton's ideas of gravity were very successful in the 17th century. It was one of the early triumphs of doing, the scientific method and putting a formula to physical phenomena. And Newton had this famous formula that said if you have two masses, they'll feel a force, an attractive force that's proportional to their masses and inversely proportional to the square of the distance between them. And Newton's theory explained why planets go around stars or moons around planets, even why apples fall to the ground. Newton himself worried about something. And the thing he worried about was what causes the influence of one mass on the other? Why do they feel each other even though they're so far apart? And this did not get solved in Newton's lifetime, and in fact not for a few hundred years until our next hero of gravity showed up, and that was Einstein. And Einstein turned our notions of gravity on their head, literally. He said gravity is not a force. Gravity is geometry. Now, what's that, you might ask? Well, Einstein's picture of gravity was that all of space-time is a grid, and if you place a massive object on this flat grid, it will deform, it will curve where the massive object is placed, and indeed, you can actually also formulate that into a rather innocuous-looking formula, which is actually really hellish to solve. So Einstein gave us this new picture of gravity. Gravity is not a force, it's warpage of space-time. Einstein also gave us an added piece to this picture of gravity, which was that, so now we know that space-time doesn't just sit around, it curves. But Einstein added another piece to it, which is that if you take a massive object and you wiggle it, it would actually make space-time around it ripple. And those ripples of space-time we call gravitational waves. So if you think of space as just a grid, and you place a massive object that vibrates on it like a star, the grid lines will deform, and these ripples will spread out from the massive object and across space in very much the same way as if you dropped a rock in the center of a still pond, and those ripples would spread out from the rock. That's what massive objects do when they are not sitting still. They have to be accelerating. That was Einstein's picture of gravity. And the beauty of this picture of gravitational waves was that suddenly we have a new messenger. Because like all other waves, they carry energy, they carry information. So maybe they could be useful for something. Now, Einstein himself did not think they would be useful for anything. In fact, in his original paper, he dismissed them as having no practical use. And that was for good reason. In Einstein's time, we did not know about the kinds of stars like black holes and neutron stars, which are very compact, dense stars that could be strong enough radiators of these gravitational waves. In Einstein's time, we knew of ordinary stars like our own star. Now, what happens, of course, to a star like our own star is in time it runs out of nuclear fuel and it kind of collapses on and forms a new, much more compact star, which is either a neutron star or a black hole. And that's just the difference between, they're cousins. The difference between them is just how massive the parent star was. If the parent star was heavy enough, more than about 3 times the mass of our sun, it would form a black hole. So that was how this business got going, thinking about gravity in this completely new way. Now, Einstein, even though he himself dismissed gravitational waves as of no practical use and was also rather ambivalent about their very existence, his theory very exactly could predict what black holes will do when they collide. So here's a nice movie that I'm going to show for those of you who can see it, of 2 black holes that are orbiting each other, and as they orbit each other, because of the gravitational waves they're radiating, those waves carry away energy, and that energy comes from the orbit. That means these 2 black holes are getting closer to each other and they're speeding up, and eventually they get faster and faster and closer and they collide. And that was a nice picture, and that you'll see in the movie. But if you look below the movie shot, you'll see a graph, and that was also the power of Einstein's theory. It could exactly predict what the signal of these gravitational waves should look like. And so here I play the movie, and what you see is 2 black holes, and they're orbiting each other. And the green and blue contours are representative of the warpage and distortion of space-time. And the 2 black holes, they're far apart, and at that time the space around them is not too warped, except right below the black hole itself. But then as the black holes get closer and closer, this warpage of space-time kind of gets much more intense. And eventually the movie will stop at the exact moment that the horizons of the 2 black holes touch each other. And if you notice the signal at the bottom that's turning blue, that's the signal being mapped out as these black holes do their dance around each other, and then it's a maximum when they collide. So here comes the moment when they collide. You can see the space-time is horribly distorted. You want to be nowhere near that system at that moment in time. But the waveform is mapped out for us by Einstein's equations. So that was sort of one of the powerful things that Einstein gave us. Among the many legacies that he's left for us was a prediction of gravitational waves and a way of exactly calculating them. So now we fast forward to the late 1960s and 70s. And in that period of time, Einstein had already passed, but in that period of time, neutron stars and black holes were just starting to be discovered. And then it became apparent that those kinds of objects, which have so much gravity in a small volume, could be very good emitters of gravitational waves. And so at that time, right here at MIT, Professor Ray Weiss, some of you might really know and remember him. He's been on the physics faculty since the 1960s. So he was teaching a course on general relativity. He was not actually a relativist or an astrophysicist really at the time. He was thinking about atomic clocks. And so he was asked to teach this course on general relativity, and as he would tell you, as has told many of us, he was only 1 day ahead of his students in terms of keeping up with the material. But he looked at this phenomenon of gravitational waves, and he understood one important property of theirs, which was that as they pass through a region of space, they distort that region of space by making it longer and shorter. And he understood that you could make a measurement of that lengthening and shortening by using an interferometer. Now, because he worked on atomic fountains and the laser had just been invented a few years earlier, he understood how laser interferometers should work, and he proposed this incredibly bold experiment that later got to be called LIGO. He also understood that if you wanted to make the signal measurable, you had to make the detectors very long. So they are also 2.5 miles long. And so here we have these 4-kilometer long detectors. They're interferometers, which means light beams travel along the 4-kilometer arms, and they are capable of making measurements. Now, this you have to really, everybody who's standing up, please sit down. You really have to grab onto your seat here. They're capable of making a measurement that's 10 to the minus 18 meters in displacement. What does that mean? It means that you put mirrors that are 4 kilometers apart, And then you're capable of measuring small changes in their distance at the level that is 1,000 times smaller than a single proton. Okay? So, and Weiss actually wrote down the calculations and the proposal for this kind of instrument by 1972. That was already written out. So, and then a few decades later, in the early 2000s, the first version of these interferometers came online. Okay, so that was the birth of LIGO, born in great part right here at MIT with our partner at Caltech, where Kip Thorne was doing the theory of how do you understand Einstein's equations and apply them to these newly discovered systems of neutron stars and black holes. Then, on September 14th last year, so in 2015, the LIGO detectors were on the air. They were actually just coming on the air after a major 5-year-long upgrade, and along came an event. And so here is a movie that shows two black holes, and the two black holes collide, just as Einstein's equations would instruct them to do. And then that gravitational wave travels across the universe. And in this particular case, we have learned it travels 1.3 billion light years. So these black holes collided 1.3 billion years ago. That gravitational wave, traveling at the speed of light, passes through our Earth 1.3 billion years later, and it causes the Earth and our detectors to shrink and stretch a little bit, just as I said earlier. And in that movie, that effect is greatly exaggerated, but the wave does exactly what it showed. It comes from the south. It hit our detector in Louisiana first. 7 milliseconds later, it hits the detector in Washington State. And those signals were recorded by this interferometer. So here's a movie of how the interferometer works. Basically, two light beams, one laser that splits into two halves, reflects from a mirror. Those mirrors change their distance as the gravitational wave goes by, and that gives us either more light or less light at the output. So all we do is measure how much light is at the output of our detector, and that is controlled by the spacing of the mirrors, and we make the measurement. And what did we measure then? The thing that we measured was this signal here. And you can see the two colors, a blue and an orange. Those were the signals in the two detectors. And they actually match very, very well the predictions from Einstein's equations. And one of the things that's interesting, so you see time on the horizontal axis. So the signal lasted a few hundred milliseconds in our detector. And on the vertical axis, you see the amplitude of the gravitational wave, which corresponds to a displacement in our detector of 10 to the minus 18 meters, just as we had designed for it. Now, in September, this signal was recorded. It turns out that in October, we recorded another colliding black hole that wasn't as powerful. And then in December, we recorded another pair of black holes, which were not as high of a signal-to-noise ratio in our detectors, but still very significant. So LIGO at this point, in that first observing run, has detected 2 confirmed black hole collisions and one that we think is pretty certain to be. And that's where we are at now. A year later, we're improving the detectors and getting ready for our next observing run. And I'll stop there and let's just take some questions.
Wow, thank you very much, Nergis. As we sort through the questions that are starting to come in from the alumni, let me first ask you to talk about your reactions to all the mass media attention your field has suddenly received this year, and whether being in the spotlight was helpful or a distraction for the LIGO team.
So I think certainly both. It's distraction may not be the right word. It certainly is it takes a lot of time and effort also to work with the media and to field all the media interest. But I have to say, in the end, no matter how much work that was, it's totally worth it. Because, it's very rare that a scientific discovery gets this kind of media attention. And in this case, I think for a good reason. I mean, it's a long-standing prediction of Einstein's. It was the very first discovery of black holes of this kind of mass range colliding with each other. So there are a lot of reasons, and everybody loves black holes, so, of course. And so it took a lot of time, but it was totally worth it. The other thing that really struck me about it was how positive all the attention was. It wasn't people saying, oh, you guys made a mistake, oh, you guys didn't get it right. There was very, very little of that. And in part, it's because LIGO has two detectors. Both detectors saw it, so they're self-confirming. And then this team of international team of many dozens of institutions, over 1,000 scientists, put in a lot of effort to make sure that we were getting it right. And so between all of those things, I think it's just been overwhelmingly positive, which is wonderful.
It definitely is wonderful and overwhelmingly positive. You all have done a terrific job of explaining to the world why it matters, too. Rick in Plymouth, we have some questions coming in, so we'll go right to the alumni questions, asks, how was LIGO Livingston affected by the recent floods in Louisiana, what we were talking about?
Fantastic question. Yes, so the observatory is fine. We had to shut down the observatory for a few days, and so thankfully it's fine, and all the subsystems have come up, and our people are getting the detectors working again. The people, unfortunately, were more affected. The Livingston Parish, where the observatory is located, I think has declared something like 3/4 of the houses were a dead loss. And so I think it's been very hard on the human scale, but the equipment and the observatory have survived fine. Thank you for asking.
Yes, it's a very sad situation. John in Silver Spring asks, are any of the G waves that were launched before the epoch of recombination, the launch of the CMB, still strong enough to be detected by LISA if it works as planned? I'm not sure I know what LISA is.
There's a lot of things here that I'll decode.
Thank you.
Okay, so LISA is the Laser Interferometer Space Antenna. So LISA is the space version of LIGO. It's not. It's been part of NASA's sort of planned missions for a long time, and also with the European Space Agency. It is sensitive to gravitational waves of different frequencies than LIGO. LIGO looks at the very fast orbits and collisions, so sort of at the 100 hertz time scale. Whereas LISA looks more at sort of the few tens of millihertz time scale, so much bigger, more lumbering systems that orbit more slowly. So you can think of LIGO as having these fast, rapid orbits and collisions. LISA is looking at the slower things. And the gravitational waves that came from the very early universe so sort of are unlikely to be detectable in either this generation of terrestrial detectors like LIGO, or also in what are the existing designs for LISA. They're very faint, and so it takes a rather significantly improved sensitivity to do that. For example, with LIGO in its present state, it would need a sensitivity that's many orders of magnitude more improved before we could see that background from the early universe. But the payoff of doing it is magnificent, because when we look at the early universe and we ask, what do we know about the universe after the Big Bang? We've collected all the information we can using light. So that's the CMB, the cosmic microwave background. Now that turns out that the earliest, earliest moment in time that light was free to stream towards us was when the universe was 400,000 years old. So those earlier epochs, times that are earlier than that, are not accessible to us by light. Light was trapped in the hot, dense universe, but gravitational waves were not. So if we could look at those, we would look back really to the earliest moments after the Big Bang. Again, it's far outside the reach of present instruments, but again, the science that you could do with that would be incredible.
Wow, that's amazing. Henry in Colorado Springs asks, what is the approximate decrease of the gravitational energy from emission to its eventual detection on Earth?
Yeah, so that's a very good question, Henry. So, at the time of the collision, of the black holes, the actual power emitted at the peak was something on the order of 10 to the 49 watts, which is really a hugely powerful event. And then the amplitude of the wave, if you will, so it declines as 1 over the distance. So it has really fallen off by a lot by the time it reaches us 1.3 billion light years later. So.
It's amazing you can even detect it. Prashant in Cambridge asks, does movement of large celestial objects through space also cause ripples in space-time? If so, wouldn't we be bombarded by so many ripples? If so, how would we be able to discern any meaningful signal?
Yeah, so that's another fine question. So the question really is referring to, well, if all objects around us are emitting gravitational waves, how come our detectors don't get inundated with all these signals and it's just a cacophony of indistinguishable signals? And the answer is that we are, at the present sensitivity that our detectors have, we aren't being bombarded by loud enough signals that they're above the background of our detector itself. So we need these very, very loud events, like the collision of those black holes that we have seen, to observe them. Eventually, as the detectors get more and more sensitive, we would hit such a limit, which is sometimes known, it's sort of known as a confusion limit, because you have so many signals coming from all different directions that you can't unconfuse them. But we're not there yet, and won't be for quite a while if our present understanding of the populations of these kinds of measurable events is correct.
So how does that intersect with the need for much more sensitive equipment in order to hear those first, or observe the first 400,000 years?
Yeah, so that's certainly going to be one of the challenges of making those measurements, is that the things that are louder and closer in will have to be removed from the signal. And eventually, there are ideas for having multiple detectors, some that are really good at looking at the nearby stuff, and then you can remove the nearby stuff from the, as the foreground of signals for the weaker stuff that's in the distance. But that's a good question.
Neil in Cambridge also asks, how do you manage to decouple the instrument from the very active vibrations of the ground?
Oh, yes, that's what we, that's a great question, and one that's sort of near and dear to me, because I've spent most of my career working on the instrument itself. So the vibration isolation is probably one of the three major subsystems of the detector. If you look at the scale of the observatories and you look at the vacuum chambers in which the mirrors sit, they're 3 or 4 times my height, and they're so huge because each mirror sits on a tremendous on vibration isolation systems. So we use both active and passive vibration isolation systems, which means the active system is easy to understand. You can measure the motions using sensors near your mirrors, and then you cancel out that motion. So if something is pushing your mirror one way, you push it back the other way, and you cancel out the vibrations that way. You can also use passive isolation systems, which are just using the properties of mechanical systems to filter out the ground noise. But that's all. You can only do so well. And if you ask, what sort of has limited the sensitivity of advanced LIGO in this first observing run and previous generations of LIGO below about 50 hertz, the limits have been that we can't remove the ground vibrations well enough. Now, in the future, as more and more of these subsystems come on, we should be able to do that well enough that we will no longer be limited by that seismic noise.
Laura in New York asks, does LIGO have a lifespan? Will it ever cease to be useful?
Yes, unfortunately, like most of us, it has a lifespan. And the lifespan is typically to do with the lifetime of the facilities. Every building only stands for so long, etc. And eventually, so our plan right now for LIGO, for example, is we're working over the next few years. I would say in the next 10 years, the present facilities are going to be our home. And we're just going to try and put improved detectors or improved technologies into the present facilities. But there's going to come a time when that may not be good enough. And in part, it's because we are also starting to understand that if you want to really look out to greater and greater distances in the universe, the detectors themselves, these interferometers, need to become longer. And so they're already 4 kilometers long, but there are ideas and proposals and dreams for them to start being 10 or 40 kilometers long. And at that point, we move into a new facility. It's very much the same way as telescopes. We started off, the first telescope that we know of was in 1609, Galileo pointed a small little 1.5-inch telescope onto the sky. And of course, learned new things. We learned about, moons around Saturn, rings. We learned about craters on our own moon, etc. So even that little telescope was a real, a game changer in how people looked out into the sky. No longer did we just use our own eyes. And now it took hundreds of years. So, from that 1.5-inch telescope, at the turn of the 20th century, we were making 100-inch telescopes. Okay, so from 1 inch to 100 inches. It took another 100 years to put a 100-inch telescope in space, which is our wonderful Hubble Space Telescope. And so I kind of see the LIGO's lifetime and facilities in the same way. Galileo's telescope is long retired, but hundreds of years later, we have incredibly more sophisticated instruments. And we're kind of like the same place. This is the first instrument ever used to observe gravitational waves directly. And now, in the coming decades and centuries, new ideas and instruments will surely be invented.
So this is like Galileo's LIGO.
Yes, I think it is, actually.
Ryan in DC asks, can you talk about the blind injections that tested LIGO staff? How did these happen?
Yeah, so blind injections are something that we, the scientists, inflict on ourselves. So what it is you take an instrument that's working reasonably well, and then a small and secret society injects what looks like a real signal into the data. Okay, and then the rest of the community faces the challenge of extracting that signal. So do we find it? Do we find it with the parameters that it had? And so it's an exercise in teaching us if we can extract signals from our noisy data. And in the previous generation of LIGO, we did that. We had these blind injections, blind because most of the searches don't know they're there. We're blinded to them being injected. It turns out that in this first observing run of advanced LIGO, there were not blind injections going on. And so we very quickly were able to remove that as a possible source of these signals that we saw, that someone had injected them intentionally into our data.
Fascinating, sort of self-testing.
Self-testing, exactly.
Mason in Boston asks, there's been talk about making LIGO's mirrors cryogenic. What's involved in that, and how might that improve them?
Yeah, so cryogenics is almost certainly going to be part of the next generation of instruments that we design. Now, why do we need it to be cryogenic? So, we've touched a little bit because of a good question that came in on vibration isolation. So the way that LIGO works is you have to do two things. Because you want the mirrors to move only because of the passing gravitational wave, you have to make sure it moves due to nothing else. And so yes, the vibrations of our Earth are a problem, and we do vibration isolation, but heat is a problem. So if the mirrors in LIGOs are at room temperature, and they have a thermal energy, and they're jittering from that thermal energy, as does everything, and that jitter, it looks like signal to us. It just looks like the mirrors are being moved, indistinguishable from a passing gravitational wave. And so one idea for, one of the ways in which you can reduce that thermal noise, we call it, is to cool the mirrors. Now, it turns out that the challenge is that cryogenic systems are also inherently pretty vibrational. Mm-hmm. So then you have to make a choice of whether, of vibration isolation that's good enough and cooling the mirrors. So LIGO does not plan to do that in this generation of instrument, at least not for the next 5 or so years. Now, it turns out there's a detector that's under construction in Japan called Kagra, which is a 3-kilometer long gravitational wave detector. And Kagra has, from the inception, included cryogenics in its design. And that will probably come on the air in sort of the next 5, in the next 5 or so years. And so we'll get our first look at operating a big detector cryogenically with CAGRA.
So it sounds like that'll be a good opportunity to understand the trade-off between...
Right, yeah, and that's been done on sort of laboratory scale testing already, but to do it on this large scale with these international instruments, that hasn't been done.
So Brian in St. Paul is asking, is there a pecking order for researchers working on LIGO? Who gets time on the instruments, like an observatory?
Oh, that's a good question. So, you know, it's not proposal-driven observing time like at a telescope. Once LIGO is, once the LIGO detectors are operating in what we call observing or science mode, then all the data is collected. And that data is shared over all the scientists who want to use it. So if you're part of the collaboration, you have access to that data. And different members of the scientific community use that data in different ways. So some people are searching for black hole collisions. Other groups are searching for collisions of neutron stars. Some might be looking for maybe signatures of supernovae. So the same data can be analyzed in different ways to look for these different sources. So it's the data is shared between all members of the collaboration at the same time.
What a remarkable collaboration.
And in fact, I'll add another thing that's remarkable. So LIGO also works collaboratively with Virgo, and Virgo is the European version. It's a 3 kilometer long detector in Italy, and Virgo and LIGO have been working collaboratively for the last several years, where we try to collect the data jointly. We try to be observing at the same time, and then analyze the data jointly as well. So it's pretty international.
That's very impressive. Bob in Chicago asks, the observed pulse seemed very short. Are there theoretical predictions of how long such a gravitational pulse should last?
Yeah, so that's a very good question, Bob. So it looks that short. The gravitational wave is actually much, much, much longer lived than that, because the whole time that these black holes are orbiting each other, gravitational waves are being given off. But when they're far apart in their orbits, the gravitational waves are at very low frequencies. So they're going slowly around each other. And what happens then is that those very low frequency waves our detectors are not sensitive to. So they're out there. They're even passing through the detector at those frequencies. But they're covered by other noise in our detector. So the time that when the waves get fast enough, when the black holes have gotten closer to each other, is when we become sensitive to them. But they're there the whole time. And in fact, if you look at the second significant black hole collision that we recorded, which was in December of last year, I didn't show the data for that, but for that one, the oscillations are in our detector for many more cycles, because those black holes were lighter, and as a result, we could capture more cycles in our detector.
Sheffy in New Jersey asks, was there anything more revelatory about the second detection in December that the first did not teach us?
Yeah, so that's a good question. I just mentioned one of those, which was that we got many, many more cycles, and that allows us to do certain kinds of science a little bit better. So the December event was not as loud. It was not as, but it lasted longer in our detector. And what we were that allows us to do certain tests of relativity in a more precise way. It also, very importantly, allows us to start building up some idea of what's the population of black holes out in the universe. Until now, we've only known about black holes of this mass range through, I would say, more or less theory and conjecture. We know that they should be there because neutron stars, their cousins, are out there. And we know that they should form when more massive stars collapse. But we haven't known for sure that they were there, how many there were, et cetera. So seeing these other black hole events has also allowed us to sort of start building a population. So I'll show one little picture that might help sort of illuminate that. So this is about what do we know about black holes? And so if you think about them just in terms of their mass, if you look on the bottom left, you see that our knowledge of black holes by observing X-rays from gas and dust that's swirling around a black hole gave us information about black holes that are quite light. They're sort of in the sort of 10 solar mass range. And if you look on the blue, those are the purple objects. And if you look at the light blue objects in that picture, you see that the ones that LIGO has seen are significantly more massive. So this is the first time that we're starting to get some sense that these more massive black holes are also out there. And one of the beauties of discovery, in my opinion, is that every time you think you've made a discovery, what you've really done is you've just asked a new question. And it turns out that we don't really understand how nature forms these 30 solar mass black holes. We hadn't known they would be out there because we don't know very well a formation mechanism. And so this is now a new area of study of how do these form, how many are out there. And these questions will be answered as LIGO and Virgo and other detectors continue to make more detections.
So I think you have alluded to the answer to this next question, but Josh in DC asks, can LIGO detect additional gravitational events other than collisions of black holes? If so, what would they be, and how often would you expect them to occur?
Yeah, so LIGO certainly can look for other kinds of objects than just collisions of black holes or neutron stars. So supernova explosions is one such example. So these supernova explosions occur when stars, again stars like our own sun or could be heavier, when they run out of nuclear fuel and they collapse, that's accompanied by an explosion, usually very bright. And LIGO would be sensitive to such a supernovae, but only in our very nearby universe, unfortunately. So if there's a supernova in our own galaxy or in galaxies neighboring our own galaxy, we would totally, we should be able to see it. So that's one kind of thing we look for. Another kind of thing we look for are neutron stars that are not part of binaries that are orbiting each other, but single neutron stars that are just spinning about their own axes. And if those neutron stars deform, and we think they do if they have mountains or blips on them, or if they just deform because they're their crust not being stiff enough, then we should be able to see gravitational waves from those. And we look for those as well. So those are the kinds of things we look for that we kind of expect, that we think should be out there. And then, of course, one of the most incredible things about what LIGO and its partners could do in the coming years is to observe things that we haven't thought about. Now, I'll just remind everybody, every time that astronomers have pointed a new instrument into the sky with the intention of measuring known things, we found things we didn't know about. And this should be no exception, I hope.
Yeah, it's hard to know what you don't know.
Right.
I'm afraid we're out of time, but on behalf of the MIT Alumni Association, thank you, Nergis, for this enlightening conversation and for your inspirational and infectious enthusiasm for your subject. Also, many thanks to our alumni for your questions. If we did not get to your question, we will pass it on to Professor Mavalvala after the webcast, and you can share other questions or comments on Twitter using hashtag #MITBetterWorld. You can also view an archive of past faculty forums online by visiting the Learn section on the Alumni Association website. Please join us next month for another session of Faculty Forum Online.